So it may be that you come across a question and your first thought might be, holy smokes, I don't think we ever learned this. But it's trying to get you to think just a little bit harder to replace something with an identity. Okay? So those are about the end of what we're going to be doing for the identities so far. I just want you to digest it a bit, work with a partner. We'll come back and do these together. But I want you to try doing these next, I think there's 5 examples here, example proofs. So there's 4 of them. This uses all the strategies we've talked about so far. So it could be a conjugate, it could be factoring, it could be replacing sines with and cosines. It could be, what else have we done? Let's see. The Pythagoras identities, it could be the basic identities, but see how you do with them. It's a pretty good summary. Start on this one. I think the easiest thing to do, because I see that there's a cosine and a secant, it might be a good idea here to expand it. So, you can always try and see where you end up. Of course, I'm going to end up with a cosine squared. And that's going to be equal to 1 minus cosine squared, which of course is sine squared theta. Okay. The next one, if you take a look at it, you probably have this feeling like you want to factor. I hope you do. Tangent squared theta, secant squared theta minus 1. And this identity, secant squared theta minus 1, can also be replaced by tangent squared theta. So that means I end up with tangent 4 theta. In the next one, there's several ways to do it. One thing you might notice that, or at least one thing I notice when I do it, is that there's cosecants all over the place here. So maybe one thing I could try is, what if I broke up this fraction and put the cosecants underneath each of them? Well, that way I'm going to end up with cosecant squared 1. And I'm going to rewrite this. I'm going to write this as cosine x over sine x divided by 1 over sine x. This identity here, this is the cotangent. So I could replace this with cotangent squared x. And on this side, I need to take the reciprocal and multiply. So those would disappear, and I'd be left with cotangent squared x plus cos x. Okay. Can I just see, have people had a chance to finish the 4th one? Okay, I'll do the 4th one, and then I know you haven't seen the 5th one yet, so the 5th one's visible in the corner while I work out the last one. In this case, again, it's almost a giveaway that if there's an exponent like to the 4th, especially to the 4th minus 1, it's going to be one where you're going to need to factor. So it'll be secant squared plus 1, secant squared minus 1, all over tangent squared theta. This one right here could be replaced by secant, tangent squared. And of course, that was what I was hoping for, because now my tangents will disappear. And I'm left with secant squared theta plus 1. Okay. So your just one other note of interest too, I guess it's kind of your nerdy fact of the day. When you do your trig proofs, I guess it's obvious to me when you're finished your proof, but there's this tradition in proof to say to the whole world, I'm finished, bask in my excellence that I've done this proof. And in Math 12, what happens at the end of your provincial exam proof, what you would do is you'd write for your marker, left-hand side equals right-hand side, so you can say, bask in my awesomeness, I've completed the proof. Where does it come from? Well, if you're even nerdier, when next year when you go to university, you may see some of your professors do a proof and they'll go like this, QED is the tradition. Does anybody know where it comes from? This is hardcore. Yes?
I forgot, but it means end of demonstration.
Very close. Yeah, it means that which was to be demonstrated in Latin. I believe, now my Latin's a little rusty, I believe it's quat erat demonstratum, which is that which was to have been shown. So basically at the bottom of it, you're like, yeah, that which was to be shown. Anyways, on your provincial exam, LHS equals RHS is usually the convention of the BAS in my awesomeness shorthand. Anyway, okay, I'll give you a couple minutes to work on this one and then we'll finish it. Okay, so one way, there are many ways to do this proof, but one way that you could go about this is to notice how many signs are in the denominator. There are a lot of sine thetas in the denominators. Cosine theta over sine theta. And on the bottom, this would be 1 over sine theta. It's very hard to start at 0 and then get into the other side. So in this one, if you look, there's sine, 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 sine. It's a pretty natural candidate to say, I want to multiply both the top and bottom of this fractions here by sine theta and sine theta down here. If I do that, then all those fractions would disappear into nice fractions, ones where there's only one line in the picture. So again, if I was to multiply sine theta onto each piece, so here and here, the top would become 1 minus sine squared theta. The denominator would be cosine, and on this side, it would be minus, cos theta over 1. So can you think of anything else that I could do? Come on, you recognize that by now, right? Sure, shout it out.
1 minus sine squared.
That's the one.
Cos squared.
Equals cos squared. So the top here, I'm going to replace this with cos squared theta. So this will be cos theta, gone, minus cos theta, which is 0. So there's any number of ways in which to do that, but I think that's probably one way to make use of that technique we talked about today.